So welcome to this short video. Thank you, Alex, for being with us today to talk about DNS security. So, Alex, first, could you shortly introduce yourself, who you are, what you do?
Yeah, sure. Thank you for inviting me as well. My name's Alex Hinchliffe. I'm a threat intelligence analyst working for Unit 42, which is part of Palo Alto Networks.
Yeah, cool. So today we're talking about DNS security. Why DNS security, Alex?
Well, I think it's probably been overlooked for far too long. It's a very powerful yet simple protocol. And often I think it's just forgotten about. You know, it's always on. People and systems need it all the time. Firewalls are typically open for those ports and protocols to allow it to work. And essentially it's like a phone book for the internet, and it allows people to resolve numbers from domain names. And I think once it's up and running, it's typically forgotten about because it's just so important to so many things. But actually, some research that Unit 42 did and published about, I think it was earlier this year, did actually say that about 80% of the threats that we see and we analyze use DNS in some way or another for their malicious purposes. And I think by default, you can imagine that if a piece of malware is installed on a system, that it would want to talk to another resource. So it might want to download another component. It might want to tell the threat actors that they are installed and can be communicated to. There could be various different things that a threat does, but typically it would involve reaching out to a domain name. And so it's using DNS. More advanced than that, we see things like DNS tunneling, where threats can actually exfiltrate data and even infiltrate data from and to the network through DNS. And as I mentioned, I think it's often forgotten about the DNS protocol. I don't think many people trawl through their logs or try and hunt the data in their logs, looking for suspicious and malicious activity.
Yeah, I believe so too. I mean, DNS, I think, is just a necessary functionality for enterprises to have in their network, and it should be there, it should work, it should be fast so that the user experience is good. So I think DNS is definitely overlooked, the risks that is in it. So yeah. So you actually wrote a blog about this, Alex, and talked about some scenarios that is relevant for this topic.
Yeah, I did. I think, and this was mainly because I think people were overlooking the security risk of DNS and how it can be used for things like DNS tunneling. So yes, you're right. I put this blog together last year, and it effectively provides a 101 of what DNS is and how it works. And you can see that in this diagram here, that a client and server are communicating through DNS, and the client is asking for the IP address of mail.google.com, and it comes back with a particular IPv4 address. And actually IPv4, to some extent, you can remember some IP addresses, but with IPv6, it's going to become a lot more tricky to do that. And in this particular example, if I talk about how the DNS typically works, that if the request is sent from the client to the server, depending on how the server is configured and depending on where that server is, there could be a log that's being generated. So all of that activity that's happening from the client to the server is logged. And in the case of a malicious activity, there could be an adversary controlling that DNS server, or at least with access to that log, that can essentially mine the data or look through the logs and try and understand what the threat's doing. And probably the most basic example of DNS tunneling is that you might see a request from a compromised system over there on the left-hand side, sending what looks like a very strange, long query to a bad site. And that long query, which is, I think, dash delimited, or some kind of delimitation within the string, if you break it up into chunks and then look at decoding it, in this case, typically things like base64 are used just to deal with certain characters. You can actually see things like the host name of the of the victim system, the username, some kind of UUID and other information. So that's the very basic examples of exfiltration of data out over DNS, and that is logged with the adversary, where they can decode that data and get a better understanding of the victim that they have compromised.
So this could actually happen even if the DNS server, for instance, is Google DNS server, or should it be a bad DNS server?
In theory, it could happen through a network of DNS servers, because there are things like resolvers and repeaters and various other parts of the infrastructure that will essentially pass the message on.
So even if you have the typical basic DNS security hygiene saying internal clients are only allowed to talk DNS with the internal DNS server, and that DNS server is only allowed to talk to one specific public DNS server, if you have that in place, you will still be vulnerable for this attack, you say?
The data could still be leaked, but it might not be that accessible to the adversary. But what we see in a typical example is once the adversary knows who they want to attack, and they've set their data up, and they've written their malware, and they've done whatever else they need to do in order to launch the attack, they would typically register a domain. And so in this example, we've got badsite.com. They would register a domain that they can control and get information from, and see the communication happening to their servers. And once that happens, then essentially the DNS servers along the way are routing the traffic for you and sending that traffic on to the right DNS server, which is the elegance of how the DNS infrastructure works. That, as I said before, once it's kind of set up and running, it's a very elegant and very simple protocol that just works. And it's that infrastructure that often the actors rely on for the data to be for the data to leave the client operating system, for it to traverse the corporate firewalls, for it to traverse the public internet and so on, and get to the DNS server. And that's where the actor would have that information and decode it, and obviously respond accordingly to the malware, essentially through the DNS protocol.
Yeah, interesting. So the basic DNS hygiene is important, is recommended, everyone should have it, but we see working with customers that if we look at the overview of which DNS servers clients are actually communicating with, we see a broad range of DNS servers being used. One of the reasons could be IoT devices with hard-coded DNS server configuration that does not care about DHCP set DNS server. It could also be the compromised client saying, I want to talk to my own DNS server. And because of all the IoT and all the dynamics in the network, you often have to have two open rule sets, two open rule sets, allowing DNS to kind of any DNS server on the internet, making it even more vulnerable. So yeah, there is a lot of risks with DNS. Absolutely interesting.
Yeah, certainly. And I think there have been threats in the past that, many years ago, decades ago, that would modify the hosts file on a system, whether it's Windows or Linux, to control where particular domains resolve. So a common example would have been threats that would want to defeat antivirus software, would redirect the antivirus update site that the software uses to get its latest signatures to 127.0.0.1 or something like that, so that when the software tries to update itself, it would just not work. So there's examples of that happening in the past. That evolved over time to malware that, once it's running on the system, could actually modify the DNS settings of the local operating system. So that's just a more modern version of modifying the host file. And then obviously, moving to the servers, affecting those as well. So there's been an evolution of kind of DNS-based threats, I'd say.
I would say it's a good thing for us, because with the modifying on the host file, we couldn't do what we are talking about now.
Right. Yeah, exactly.
And the good thing with DNS today, generally, is that DNS still is clear text. It's going more and more over to encryption, but it's still in general clear text. But with the DNS over HTTPS or DNS over TLS, we can still do this stuff, right? We can still do the inspection and control, right?
Yeah, in theory, if you can decrypt the SSL traffic and you can understand that, then that's doable, certainly. And I'd also say that there are some aspects of threats that I guess reveal themselves more than others. So if you've got a piece of malware that talks once to a domain name to try and download a file, to resolve and find the website, find the server and download another payload, that's potentially just a one-off operation, and it might be harder to see. But in the case where DNS is being used for actual command and control, or C2 communication, which is almost a constant kind of back and forth between the client or the victim with the malware and the server and the adversary on the other side. If that communication is happening quite often, you could actually start looking at more data, hundreds of records, thousands of DNS queries, to try and extrapolate out and understand if there's a pattern occurring.
Yeah, it's fancy. I must say it's fancy. Would you like to? Is there anything more you would like to present in the blog, or would you go to the Xhunt story?
Yeah, well, just quickly in this example here, which is more about infiltration. So there's the same kind of query that we're seeing from the compromised system to the server, and in the response, instead of it just being, say, an IPv4 address, and they typically map to things like instructions. So if the IP that's returned from the server is 1.2.3.4, it's likely that that's not an IP that would actually resolve for the purposes of the attack. But the malware is programmed to say, if I see a 1 in octet 1, it means download a file, or it means delete this file, or it means uninstall myself, whatever it might be. And obviously you can think of hundreds, if not thousands, millions potentially of instructions that could be encoded into a 32-bit IPv4 address that the malware is pre-programmed to understand. But there are other examples as well. So things like text records potentially could be used, where a large amount of data could be sent either off the client or infiltrated into the network to the client. And this could be like another payload for the malware to run. And it would take the text record, decode it, and it would have some code or a binary to execute. So that's just an example of how a lot of data could be potentially infiltrated.
And this, of course, is what you present here now is what's actually doable in theory. But
yeah,
you've actually seen this in the wild, right? So you've seen this in real life, that this tactic has actually been used to do damage.
Yes, and it didn't just start with Xhunt, this particular example that I happen to talk about now, but we've seen it with other threat actors in the past as well. I would say DNS tunneling tends to be a technique that's used more by, I guess, advanced adversaries, possibly APT, to use the APT notation, maybe nation state, more targeted attacks that are more specific in nature, more targeted in nature, and perhaps want to try and stay under the radar. Conversely, if you think about, ransomware, a commodity piece of ransomware, or a very prevalent piece of malware like Hansator or TrickBot or Emotet, those threats tend to not necessarily be very targeted, and they tend to be quite noisy, the volume of them. So there are certain threats, I think, that use DNS tunneling. And in this particular case, we discovered this threat that was attacking one of our customers. And in the usual way that we do our investigation and research in Unit 42 is if we find a sample, we'll try and pull the sample apart, we'll do some reverse engineering, we'll write some Yara signatures, we'll do some hunting. There's various things that we always do to try and understand the picture, and if it's a bigger picture, and if if there's more samples to find and more infrastructure to uncover. And in this particular case, in parallel to Unit 42 working on that aspect and the general threat research, an engineering team in Palo Alto Networks, who is in charge of a relatively new subscription we have called DNS security, were also analyzing data that was coming in from our customers' networks who were using this subscription. And they actually found the threat, pretty much in parallel, which is a fantastic use case, which shows that some of these technology advancements like DNS security really do work in kind of elevating the security of a typical organization, especially when it comes to DNS, which we've talked about, that tends to be overlooked. So in this particular case, in the X-Hunt campaign, the threat was delivered in a usual way with a phishing email and using kind of social engineering and those kind of things. We also saw then when the payload was installed, in this case, it was called, or we called it Cache 200, and it was a threat that was installed on the victim system, which then started communicating using DNS. So this picture here just shows an example of what we saw in our internal labs when we were analyzing the threat. And what you're seeing is essentially the DNS query going up and the DNS response from the server all in one picture. So you can see the domain here, which, once it was registered and used maliciously, over time that would become known as a malicious domain, and it would be easy to block it using traditional methods like threat prevention and kind of known good and bad lists, essentially. So you could say this domain is bad, so we're not going to allow any communication to it. But in the run up to that domain name being discovered and being classified as malicious, there's a period of time, and it could be minutes or hours, it could be weeks or months or years potentially, where people may not be able to detect that suspicious activity happening. In this case, we're seeing what looks like random data being sent to these queries, and perhaps many years ago, this would have looked like a very suspicious looking query. But actually nowadays, with things like session IDs and single sign-ons and cloud infrastructure and loads of other things that are all network and domain based, looking at, it's fairly typical to see queries like this happening all the time, I'd say. So you've got some random numbers first, or random characters first, potentially just to throw off researchers and detection systems, to make it, to make these DNS queries not look too similar. And then the rest of the data in essentially that subdomain, if you like, before the first period symbol here, so any of this data on the left, is then encoded data that includes information about the victim. So there's like a unique identifier. So if the threat actor has 10 victims, they can start to pull the data apart and understand what's happening on one victim versus another victim. And then in this particular case, the first query that goes out is like a heartbeat to say, we've managed to compromise the system, we're alive, what should we do? And often the first response back is to, initiate some kind of further command, like to get some basic system information. So it could be that the host name and the username and other information is sent up to the server, and then another response comes back. In this particular case, there are a couple of three queries here in the middle that are of interest. So one of them, in this particular case, the 92.2 tells the client to execute a command, and the 2 here references the number of queries that will follow or that are required in order to get the command. So you can see the first query here with the response, and the second query here with the other response. And those decimal numbers, if you convert them into ASCII, actually translate to the "who am I" command. So essentially the server is saying execute the "who am I" command, and then the results of the who am I command are coming up here in this query. So you're essentially exfiltrating the username and the system name of the victim.
Fancy. And this is a real example.
Yes, this is the real example. Like I said, there are many different threat actors that use the same kind of techniques. So DNS tunneling for their command and control traffic, and that they differ vastly. So some of them have lots of subdomains, with each subdomain depicting a particular command or a particular piece of data to be exfiltrated. And this one, I think XHunt typically tends to have all the data that's needed for the command, and then simply the domain name. So there are millions of different ways that you could essentially create your own DNS tunnel protocol, but ultimately that's what you're doing. You're tunneling some information over another protocol.
Cool. You mentioned briefly also what I like to call fast flex domains, which, I mean, this tunneling part, as you also said, is perhaps more common in the more targeted attacks for the large enterprises, for the more critical infrastructure owners, and more targeted, while the rest of the society that is perhaps not in that targeted area can also be hit by stuff where DNS is used to actually reach the attacker's goal in perhaps form of fast flux domains, etc., etc. What else is it in DNS security that is crucial for people to think of?
Yeah, so that's an example, fast flux, and also things like DGA, or dynamically generated algorithms, where essentially a particular threat which may compromise a system could have a list of domain names that it would try and talk to, and they are dynamically generated. So it's not like they are known ahead of time, or it's not like they are predetermined in some way that's easy to extract and to analyze and to detect. But essentially these threats give themselves multiple opportunities to be able to communicate out to domains depending on, you know, the time of day or the day of week or whatever it might be. There are algorithms built into the malware that are also known at the back end, or where the adversary is, to coordinate when the malware will communicate and to ensure that the right domain is actually up and running. So I think some threat actors probably cottoned onto the fact that if they stand up all of their infrastructure at the start of the campaign and all of their infrastructure becomes known quite quickly, that essentially the malware is neutered because it can't communicate where it needs to. But actually, if most of the domains aren't registered yet, or they're not up, so that you get a non-existent domain or NX domain response from a resolution, then it's not as easy for the defenders like us to detect those kind of threats until they start communicating. So yeah, there are many different ways to try and, you know, abuse DNS, or to use it in a smart fashion to try and evade detection, essentially. And that's going back to my very first point about trying to scale up and automate the protection around DNS, much like we do around files and things like that we analyze in a sandbox automatically, and try and make automated reputation verdicts for and things like that.
Yeah. So wrapping up here, I think the last thing you mentioned regarding fast flex domains and DGA against malware should also be relevant when it comes to phishing, right?
Yeah, certainly. Anything that revolves around domain names on the internet and things like that would also fall into that category.
Yeah, exactly. Great, Alex. I think we end it there, and I hope that the listeners have got something new in their head now when it comes to DNS, and I hope that the listeners will actually think of DNS more seriously and take the security part of DNS more seriously, and take action on that, and don't just let it be a functionality that's always there and it's just works because it's, yes, it works, should work, but it's also potentially dangerous.
Yeah, agreed.
So, thank you very much, Alex. I think we end it there, and we'll talk to you later.
Thank you very much.